for this program. Before I take any much of your time, I would like to give a brief introduction about our speakers to the delegates. So, delegates, Professor Amit Garg specializes in energy, climate change, and sustainable development issues and offers courses titled Carbon Finance, Managing Energy Business, Sustainable Finance, Energy and Environment Policy, and Public Management. His current research interests include carbon and climate finance, energy businesses, corporate accounting of greenhouse gases, energy and environmental modeling, water energy nexus, and preparing businesses for climate change challenges. He has co-authored 12 books, 25 international research reports, and published extensively in international journals. He's a lead author for 5 reports of the UN's Intergovernmental Panel on Climate Exchange and is currently the co-chair of IPCC Emission Factor Database and co-editor in chief of Carbon Management Journal. Our next speaker today, Dr. Naran Pindoria, is from IIT Gandhinagar. He is an associate professor in electrical engineering at Indian Institute of Technology, Gandhinagar. He was a research fellow in the Department of Electrical and Computer Engineering at National University of Singapore in 2010 and received a PhD degree in electrical engineering from IIT Kanpur in 2009. His focused research interests include electricity market, smart distribution grid, microgrids, and grid integration of distributed energy resources and energy management. He is currently a co-PI for national and international collaborative research projects and recipient of IEEE Power and Energy Society Gujarat Chapter Outstanding Engineer Award in 2017. Our last speaker today is Shri Srinivas Cherla from Research and Innovation Circle of Hyderabad. He's an alumni of IIM Ahmedabad and has worked in the US and India in technical and leadership roles and is currently the Director of Sustainability at Research and Innovation Circle of Hyderabad. He has over 15 years of industry experience spanning energy, electric mobility, and manufacturing sectors and has worked on consultancy projects involving market studies, developing go-to-market strategies, applying socio-economic frameworks, and synthesizing business models for corporations. Few of the notable organizations that he has worked with are Convergence Energy Services Limited, Indian Institute of Management Ahmedabad, and Innovation Norway and UNEP. Ladies and gentlemen, these few words cannot justify the immense experience and expertise the experts has, but I assure you all are in great hands for today's program. Now, my last information to all of you that we have muted you to avoid any disturbance to the presenter. After the presentation is over, we shall be unmuting you and then we can have the interaction with the experts. So without taking any much more time, I would like to hand over the panel to Professor Amit. Sir, over to you, please.
Thank you very much. Am I audible? Yeah.
Yes, sir.
Thank you. Now, welcome to all the delegates and participants of this event. This event is one of its kind, I would say, which has been organized by CBIP. So we are very thankful to Shashank and his team for organizing this event. Energy systems are changing all over the world. In India also, the big Goliaths, which are the energy companies, big companies, are being challenged by small Davids, which are the upcoming micro enterprises that are coming up. So this we are trying to say whether we can expedite this transition and then transformation through blockchain. What are the applications possible using blockchain on this? And we'll talk about grid edge to systems operation, the complete thing. Professor Naran Pindoria and Srinivas Cherla, they are very, very expert in these domains. I'm just sort of giving a broad overall outlook to you all. And then I would hand over to Professor Naran Pindoria to take you through, and then, of course, finally, Srinivas to take you through what we did. So next slide, please. Yeah, okay. Ecosystem transitions. Please keep it there. So this slide shows what are the current ecosystems, how the power generation is coming to our homes, our offices, our industry, and then how the future is happening. And future is now. They very quickly we are changing to distributed generation. We are very quickly changing to real-time decentralized markets, which may not have happened so quickly, but are happening as we see all over the world. We are having localized power consumption. We are seeing bidirectional power market. That is, you can produce power, you can consume power. So you are called prosumer, producer and consumer simultaneously together. So this is happening, but this bidirectional power transfer requires changing the network, putting them, providing them capability to handle bidirectional flows. Power flows may be simple. We just step up the power and send to the grid. But the point is, how do you account for this? How do you keep the grid stable with all these distributed generators coming into? And that is something which is becoming a challenge. Of course, these are things that we see a lot of things happening out of these, especially distributed generation, especially smart meters coming in. Smart grids may not be time of day pricing, is not coming in India for you and me, but it may be coming. So these are systems which are falling in place slowly, and then maybe the big ecosystem is emerging. Next slide, please, Srinivas. Blockchain for energy companies. Now, I trust you have some idea about blockchain or may have seen. Blockchain is a, I think, how would I say? This is something which cannot be
Immutable.
which cannot be, which is a immutable record, which is shared through multiple consumers together, multiple partners together. So no one person can play maybe any mischief with the system, because all data has to be changed with all, which is not possible. And once a blockchain node has been established, it remains so until the regulator says not required. So power systems are very, very specific in this domain. We will see how we have done this. I think Naran and Srinivas will talk about it. So some of these things which are pain points for power companies, billing. Now utility companies normally receive their payment after a month or 45 days of billing cycle, and that time, until that time, they have to bear the cost. And the producers who supply their power to companies, energy companies, utility companies, they're also kept on hold. So this makes the whole system a little inefficient, because money is stuck up in the system. So whether we can make this billing real time and settlement can happen on a daily basis, something that has to be seen. Sales and marketing, we have to apply artificial intelligence to identify energy patterns of consumers, because we don't know how much we are consuming now, what time we are consuming now. So if blockchain based AI is applied, we will have a better I think assessment of demand of power for any time, and then that will also give more handle to the utilities how to get that power in time, and then pricing also can be managed. This also gives rise to something called demand response, which is if the at peak time lot of demand for power is there, can the utility company request or demand a reduction in power by its consumers, and then the consumers can respond and say, okay, we will reduce the power. And that time the maybe power prices could be as high as 17 rupees per unit, but you and I, with as residential and commercial consumers, will not pay so much, maybe 8 rupees, maybe 11 rupees at most. So the differential of 6 rupees has to be borne by the companies, which they want to reduce because it is on their bottom line, Wholesale market management, commodity trading, risk management, all these things, of course, with the carbon markets coming in, green infrastructure coming in, there is a demand for making the systems more efficient. As the systems become efficient, everybody gains because the losses come down and the efficiency gains are reflected in financial gains. Automation, of course, lot of automation is possible. You can see everywhere automation is happening. So same thing, we are also thinking that whether energy companies can also look for some automation, can take some automation, which would be good for the system. Next slide, please. Yeah. To continue further, smart grid applications, data transfer, because data is very important. Once you put a smart meter, you know the demand pattern of every household, how their consumption pattern of every household. This is big data which can be used and transmitted. So on these type of smart grids, there will be three levels, three layers. First will be the fundamental power layer. The second layer will be the IT layer, and third layer will be all the equipment providers like smart meters, like other systems. So power layer will definitely be there because finally you have to transmit power, receive power onto the grid. But IT layer, which will manage the data, which will manage all the whole operations, will be required to be interfaced with the power layer. And of course, there are many multiple players who are providing instruments and supporting systems, hardware, software. So all these have to come together. A smart grid. Grid management, of course, blockchain would provide maybe better network management, because with more of rooftop solar, more of distributed generation coming in, we have to estimate that when the grid load will be maximized or people will start using their own power. So I think anticipation of total grid, what we call is the total load curve, would become a challenge. So it will be good that there is some system which is real-time monitoring our grids. Like if you look at your laptops is like whenever the power goes down, it sends a signal or switches off something or reduces the intensity of the screen. So this is like operating and sensing the power backup the system. Same way, smart grid has to sense real time what is the load, what is the supply, and then match them real time. Of course, as we go deeper, you know that 2G, 3G, 4G, 5G, the security requirement goes up. Same thing as you go deeper with the smart grids, with the application of blockchains, the security requirement would go up many times. So that is also an expense, but that is also a security that systems will not fail, they will continue operating. Of course, resource sharing, that we can even do electric vehicle bi-directional charging. Professor Naren Pindoria has done tremendous seminal work on this. I think he will make some presentation, he will let you know. So this type of EV charging, this type of distributed generation can be shared. And of course, there's something called smart contracts. So whenever you draw a blockchain based system, then you can draw a smart contract in advance. So whenever those conditions which are governing smart contracts are met, automatically the contract will be entered into automatically. So you need not do a lot of to and fro for this type of thing. Of course, immutable records and transparent processing, they provide a lot of transparency and maybe faith in the system, because many times people don't know from where you are buying. So that faith and trust is generated through these contracts, smart contracts and transparency. Next slide, please. Yeah, so these are some of the application areas. There may be more than twice than this areas, but I will go through very, very quickly. Optimizing customer energy cost, because once you know the demand of power and supply of power, you can optimize the whole system. You means the system can optimize the energy cost. Then grid settlement can happen every day very quickly. Whatever is additional which have been drawn by somebody, whichever has been supplied more by through the grid operator, or somebody has not met their supply commitments, that all can be settled very quickly as and when on a daily basis, by that is once in 2 days basis, weekly basis, whatever is possible is third is real-time power trading at the energy exchanges. There are 2 energy exchanges now, IPX and IXEL, and about 90% of power in India is traded through long-term contract power purchase agreement. So 10% is traded through these exchanges. So this may normally if you buy power on the exchanges, it is more expensive because it is called a spot purchase. So if we do set up these systems, I think the trading and energy exchanges will become more efficient. Maybe we'll discover the prices that are better. We can do that. Then fourth is peer-to-peer trading among prosumers. Prosumer is prosumer and consumer. Producer and consumer together is prosumer. Microgrids. So all these things, when you have a rooftop solar on your building and you want to sell some small amount of power to your neighbor when you are not using it, or want to sell it to the grid back, there is a possibility that through these blockchain applications we could do that. We did something, and I think Srinivas will explain this real-time case. Then electric vehicle charging is a very big thing depending on the size of the vehicle. Maybe it is 100 kilowatt hour or 27 kilowatt hour or even bigger. Now big vehicles are coming which may run for 250 kilometers at a stretch. So they will have bigger batteries, and those batteries can provide charging to houses, minimum charging to the houses, maybe minimum electricity charge to the houses for some time. So that type dual bidirectional, that is you charge vehicle and also feedback to the system once when required. Smart contracts, as I said, are financial transactions which will be automatically entered into if we are going through blockchain route. Next, please, Srinivas. Yeah. So this is what we had a project which was funded by Department of Science and Technology. It was international project which had multiple institutions. So IIT Gandhinagar is there, Ramaiah Institute of Technology, Bangalore is there. We are there, of course, and BSES Yamuna Power Limited is there through their 2 bodies, through institutions. Then Renault is there, Amplus Solar is there, and of course government of Telangana became a partner, and there is also Florida International University in the US and Innovations Norway. So this is a very big project which we ran for almost four years, and the project is coming to a close very shortly, and we have done many things which my colleagues will now make presentations on those parts. So yeah, so I hand over to Professor Naran Pindoria, and then he will take it forward. Thank you.
Thank you.
Thank you very much, Professor Garg, for setting up the context of the today's discussion. I hope I'm audible to everyone.
Yes.
Yeah. So, like as Professor Garg mentioned, that electricity sector has been undergoing to the massive transformation towards three Ds: decarbonization, digitalization, and decentralization. And through this project on development of prosumer-driven integrated smart grid, we are trying to demonstrate how 3Ds transformation can be integrated or can be in the energy sector. So moving forward, let us try to understand the decentralization aspect in energy sharing or energy trading. One can clearly look at this figure wherein like the community having the multiple residents, that residents may have the on-site resources like solar PV, rooftop solar PV, stationary battery storage, or electrical vehicles energy storage, and the flexible demand like the thermostatically controlled load, maybe air conditioning, or even the geysers application. So we try to leverage the flexibility from the on-site generation and the demand, and how that prosumer who has the ability to produce the power locally, and as well as the consumer can get the benefit out of that if we provide the platform wherein they can able to sell the surplus power to the neighbor instead of selling power back to the grid. And that's how try to matches the generation and demand as locally as possible, and get the socio-economical benefit through this peer-to-peer energy trading platform. So trying to develop the decentralized way of energy sharing at the consumer level itself. That consumer could be residential consumers or the kind of residential society where the consumers can participate to this P2P energy trading platform, or they can make the contract with the aggregator. Aggregator can be the contact point with the utility and try to set up the decentralized marketplace for energy trading or sharing among the participants. And that can be further extended to the microgrid setup, wherein multiple prosumer consumers at the high power level can perform the similar activities, and all the financial transactions, all the power transactions be logged in the very transparent manner. And that's how we try to integrate how these financial transactions are being logged in the blockchain. So that's how, if you see the figure on the right hand side, where we try to create a kind of the skeleton where we see how the different level of community can participate in the energy trading platform. And that platform provides the tool wherein the participant can see the all transactions, the power transaction to the neighbors, different peers, and how the financial benefits. So this provides a full balance techno-economical empowerment to the prosumers, consumers, and even the grid operators, meaning the utility. So all stakeholders get the benefit out of that. So this gives the just a kind of the overview about what is P2P, peer-to-peer energy trading in a nutshell. We will try to understand in a much detail while considering maybe the residential consumer first. But before going to the single home, let me give you how the peer-to-peer energy trading benefit to distribution system operator or distribution network operator as well. Because many of you are maybe from the network operator point of view or utility point of view, and you may be handling the portfolio at the utility level. So the point here is, if we create a kind of decentralized framework for energy sharing, how the DSO can get benefit out of that. So now very first, the technical challenge that we all are facing is overloading and the outage of DT. Outage of distribution transformer is most often happen because of the overloading of the transformer. And it's very important valuable asset in the electricity value chain. And all the utility try to have a minimal downtime of this utility. So that's the preventive maintenance play the important role here. So with having a local or decentralized trading at the consumer level itself, whether that consumer is residential, commercial, or industrial, CNI consumer, or even the agriculture level of consumer, how we try to have the energy sharing among themselves so that the loading on the distribution transformer can be minimized. And that's how we try to have optimal loading on DTR. Then the second is the cost benefit analysis to this distribution system operator. Given the fact that in one of the Ds, we said the decarbonization, we promote more and more decentralized renewable energy based electricity generation. We say the DER integration, right? Distributed energy resources, which also includes the battery storage, in addition to solar PV based generation and the other sort of generation, the green energy generation. So how we try to get the benefit of that? The solar PV based generation, we know is intermittent in nature. But what happened? Luckily, we get the peak power generation when we have a peak demand. So it's highly coincide with the generation when the solar PV is available. So how to have the peak load management? So by having the local level control through this P2P energy trading platform, we try to minimize the peak. So the peak saving or managing the peak at the distribution network level is the key challenge. And we noticed that the P2P energy trading and the another program, which is called automated demand response, that we executed through this project at a different utility. And I'm going to present that also in next few slides. So the cost-effective energy alternative during the peak demand event is one of the other benefits that we notice through this project. The third is the benefit by not having to purchase surplus energy export back to the grid, right? We know that all the excess generation at the consumer end used to feed back to the grid, and the bidirectional power flow lead to the technical challenge to the distribution network. The distribution network may not be well equipped to evacuate that power back to the grid if the power quantum is really high. If we ask this question to the residential consumer, the export of the power to the grid is not that high. But imagine if that power has a considerable amount and the quantum, whether the grid is equipped to evacuate that power while considering the technical feasibility, meaning the voltage regulation and the frequency regulation intake. So the alternative solution is provide the local energy trading platform and let the energy sharing and the energy settlement within the community, within the microgrid, so that the export-import from at the consumer end to the grid can be minimized, and that may resolve multiple technical problem that grid may face when we have a higher and higher penetration of distributed energy resources. Then the second is from the economics point of view, revenue point of view, DSO gets the revenue because of the transaction fees, because the transmission corridor, the distribution corridor, the wires, the power transfer is still through the asset developed or laid down by the government agency or the private agency. Basically, it's a utility. Now, utility will certainly charge the willing charge to transact the power from one peer to another peer and vice versa. So the utility get the benefit out of that. So the asset utilization is being maximized if we try to have a local power sharing among the peers. Then this would lead to the role of aggregator, like as we saw in the previous slide, that the community aggregator comes into picture, and community aggregator on behalf of those prosumers and set of prosumers and consumer can participate in the peer-to-peer energy trading with the another microgrid nearby. So that's how there is a active participation, or there is a potential opportunity for the aggregator to participate in this program. So that's how we get the benefit to the DSO through decentralized power trading platform. Moving forward, let me now try to indicate what all are the key components and their interaction if we consider the single home. I will start with a single home and then create the different peers. to understand the entire. Here is what we see, like the typical prosumer having the rooftop solar plus stationary battery, I mean the storage, and we say that vehicle that prosumer having the EV charging infrastructure, so that EV storage, EV battery can also be used here if that EV battery has the bidirectional converter, so that EV can act as a vehicle to grid, meaning the excess energy stored in the vehicle can be feed back to the grid, and that or to the sell out to the another peer. So that's how we leverage the benefit of the energy stored in EV battery. So this is about the resources, on-site resources at the home. And what we need, we have the power consumption appliances. Nowadays, we know many of these appliances come with the smart controller. And if not, then we require some smart plug to make it controllable, so that we can have the real-time decision making. And then how to generate that real-time decision making through application of artificial intelligence and machine learning algorithms. And that's how we integrated AI/ML algorithms, so that the consumer can make the decision in real time and make use of the on-site resources more productively and improve the ROI. So, the point here is when we invest money on installing the solar PV and having a EV infrastructure at our home, whether it's a two-wheeler or three-wheeler, and if we can't use those resources optimally, we may not fully utilizing their benefit, and that's how the ROI may affect. So here is like we would like to create a framework wherein we optimally scheduling the resources, so that that consumer or rather prosumer have or get the benefit out of that. And that to make the decision, we build the smart agent. So the smart agent has the smart agent provides the gateway to the peer-to-peer energy trading platform, which we created, and the prosumer will have the mobile application to schedule. I mean, the mobile application where the consumer see all the energy assets data point, what is the generation at what time, how much is generation from the solar, and how much would be the generation tomorrow. So even the smart agent provide the forecast of the solar PV generation, what would be the state of the charge or the battery, whether it's a stationary battery or EV battery, and likewise. And those all data we process locally and take the decision that what should be the optimal scheduling of the flexible resources, whether it's a generation or load, so that the prosumer get the benefit out of that. And then once the prosumer has that decision making, then prosumer can make a contract with the another peer through blockchain gateway. And that's how the gateway, the blockchain provide the data recording, transparency, and everything. And we have inbuilt analytics tool, so that the consumer can see and assess the data and understand how optimally these gadgets are being utilized, right? And the other facility like messaging, then the financial settlement, techno-economical assessment of the own assets, everything are inbuilt in our platform. So this is how it's just a narration of understanding the single node having the residential consumer equipped with the different resources. So moving forward, let's see how it works and how we demonstrated this through a POC and the test rig at IIT Gandhinagar. Let me explain the sort of the schematic layout on the left hand side of the figure here. We see the peer A, B, C. Peer A has a solar PV of 3.5 kilowatt and the battery energy storage of 7.5 kWh. Wherein the housing load, which has the typical load like a ceiling fan, tube light, TV, computer, air conditioning, split AC. So those kind of residential appliances. And some of these appliances are connected with a smart plug because we wanted to leverage the flexibility of the thermostatically controlled load like air conditioning, so that the consumer can able to sell out more power during the peak hours. So that is about Pier A. Pier A is connected with the energy meter, and this energy meter is a typical energy meter. If you try to see the actual infrastructure on the right hand side figure, where you see the 2 dBs, Pier A main dB, which is the incomer coming, and then net meter is connected at the top, which is bidirectional net meter. And then Pier A, the load meter, which is on the left hand side dB, and the output is the meter. At the output meter is connected, which monitors the load connected at the Pier A. As I said, the load at the Pier A are those load appliances. Appliances are our typical home appliances. Then the Pier B on the left hand side figure, if you see the Pier B has the EV, electrical vehicle, but this electrical vehicle is equipped with the bidirectional EV charger. What does it mean? That the vehicle can be charged by buying the power from, let's say, Pier A. Whenever the Pier A has excess power, and deal with the or contract with the Pier B and charge the vehicle through the solar energy instead of buying power from the grid while charging the electrical vehicle. But at the same time, what if the vehicle comes back at a home in the evening and vehicle has the excess energy store, surplus energy stored in the EV battery, and Pier B say, okay, how about I sell this power to the Pier C if I'm getting the more economical benefit? Then vehicle can be plugged in with a bidirectional converter and sell this power to Pier C or Pier A or to the grid, and get the benefit of peak hours, peak price, and charge this vehicle during the off-peak period in the night and ready for driving tomorrow morning. So that's how the bidirectional converter facilitate the EV vehicle owner to sell out the power and get the economical benefit during the peak hours time at the set price. So is this price, please note that this price are mutually decided between the peers. It's a contract price between peer to peer or so. But please note that the power exchange, the power flow is through the corridor which are built by the society or by the utility if we talk about microgrid to microgrid, right? So this is how the infrastructure built. The Pier C is the typical consumer. The Pier C doesn't have the solar PV, doesn't have any other resources, generation resources. It's just a consumer. So we say Pier A and Pier B are the prosumers, meaning they have a production capability as well as the consumers, whereas Pier C is just a consumer. And now the important part here, if you see the typical meters we use in the practice, whether it's a residential meter or the commercial meter, all come with the these are the digital meter, but they don't have a capability to make the decision, right? So we wanted to create that, or we wanted to empower, or we wanted to build that infrastructure through add-on device. We developed our own smart agent which log the data, energy data, all sort of data through the meter, sort of generation data at every 15 minutes interval, and we can even tune that data logging facility of every 5 minutes interval, even 1 minute interval, as long as the meter sensors and meters are capable to log the data, whether this is electricity data, solar irradiance data, weather data, or solar generation data. Then we receive this data. Srinivas, if you move forward. So this data, okay, sorry. One more slide, please. It's a different slide, but anyway, if you go back to the previous slide, Srinivas, yeah. So we process this data internally. So for instance, if you look at Pier A, which has a hardware layer I have explained in the previous slide. Now the control layer, so whatever resources are controllable, whether it's a generation resource like a solar PV is not the controllable resource, but the battery storage, the charging and discharging, that is under our control. We can try to charge and discharge through BMS, right? Battery management system. So it's a controller is there. Then in a software layer, we process the data, raw data coming from the sensor. Then we forecast the solar PV generation for tomorrow, load demand for tomorrow and in next hour. So we forecast in a day ahead. We forecast for an intraday event also, just 2 hours before the actual event happens. And then based on the forecast information, we have to make a decision at that what time and for what capacity I should charge or discharge the battery, whether that battery is a stationary battery or electrical vehicle battery, right? And once that assessment is done, now peer A can make a decision that whether I should sell that power to peer B or I should buy the power, and that decision would be based on economic objective, or the economic objective saying, okay, how to maximize the profit while I make the contract to peer B, peer C, or with the grid. And this all information exchange and the data are recorded in a blockchain gateway. So the smart agent provides the gateway to the blockchain. Blockchain is a server-based application. Now every consumer will consumer has the kind of the consumers who have registered in the peer-to-peer trading platform will provide the have the mobile application where all the data the consumer can see and try to make the contract or try to trade, submit the trade, whether it's a sell bid, selling the power or buying the power at a particular time window, whether 15 minutes, every 15 minutes interval, one can schedule that, right? So this is what the building block diagram of the entire P2P energy trading platform that we created at IIT Gandhinagar, demonstrating this POC. So demonstrating the P2P energy trading platform through POC, wherein we consider 3 peers. Moving forward, so just to give a very insightful discussion about how exactly the peer A is equipped with in terms of the sensors, energy meters, and how exactly the smart agent work. So if you look at the right hand side where the SLD single line diagram is given, it's a 3-phase connection. Certainly, it's with a 415 network, it's a LV network at IIT Gandhinagar, which a net meter is connected. And then at a common bus, if you look at the, and if you recollect the physical connections that we showed in the previous slide, so the residential load with the air conditioning and the tube light, fan, computer, and so on and so forth, with the load meter, and that meter feed the data through RS485 communication. So the meter is equipped with the RS485 communication port. As I said, it's a digital meter. So certainly either RS485 communication, Modbus, or the DLMS meter, right? That widely used in our practice. So RS485, that data feed to the microcontroller that we program. So we receive the data. We fetch the data from all the meters, and similarly from the solar PV meter we fetch the data. And then the battery storage. So battery storage. Now out of these resources, battery storage is the flexible resource. We can control the charging and discharging. So that's how all the data feed to the microcontroller. We process the data, the historical data, and based on the historical data, we develop the forecasting module to forecast the solar PV generation, electricity price forecast, and the load forecast. And based on this forecast, we derive the decision. And for that decision, we develop the optimization framework, and this all forecasting module, optimization module, all run in the sequential manner within the smart controller. It's like a generalized the smart controller, and it's very cost effective and very compact. So, and that we call a smart agent, which provides the gateway to the blockchain and the sensing. So this is what the entire architecture of the single, the peer, which is equipped with a smart agent, because meter cannot give the decision, right? So to enhance the capability of the meter, we have developed this and integrated with a proper handshaking in the communication protocol and everything. So this is what the nutshell about this. So let me present the key takeaway messages from this infrastructure. So in fact, that I have already discussed. This is what the smart agent has: a 3 sequential module: data processing, then the forecasting, the algorithm, what all algorithm we have used, machine learning based algorithm we have used, and then that forecasted information we pass on to the optimization module, wherein we expect the decision making or decision to schedule the flexible resources, right? So the controllable resources like a distributed energy resources, we used to control so that the prosumer would make use of or better utilize the on-site resources, right? So with this, let me present the result outcome in the next slide. So so now, as I said, the consumer or prosumer who have signed the or registered with the peer-to-peer energy trading platform, they will be given the mobile application, wherein the mobile application during the onboarding of this consumer or a prosumer, we ask the prosumer or consumer to log all the detail about the infrastructure, solar PV generation, how much capacity, what is the contracted demand or maximum load, what all are the loads at the home, whether it's a consumer having or prosumer having a battery storage, which type of storage, and the capacity, everything. So that is onboarding. Once the onboarding is there, now consumer know that based on the meter data and the forecasted, the smart agent give the scheduling. So that is automated. And that prosumer will submit the sell bid and the consumer will submit the buy bid for a all 15 minutes time interval block. So here is the case that I want to present. It's a specific case that we ran the case sometime in 2020 on 27th May. The peer B wanted to buy a power of some unit, and the peer B load profile I have given here. As I said, these are the small consumer, but the peer B has the demand because peer B has the water pump. So that pump, the evening cycle around 6 p.m. or 6:30 p.m. that the peer B needs the power. Now, instead of buying this power from the grid, peer B made a contract, or submitted the buying bid at the P2P trading platform, and peer A say, okay, I have a power because I stored the solar PV generation during day in my stationary battery, and I would like to sell this power out to the peer B. So that peer A created a trade of 1 unit of energy at 6:30 p.m. to 7 p.m. on 27th May 2020. And that data log you see in the mobile application window, if you see on the right hand side, right? So moving forward, like how that was done in the backend, how it was done at the backend. If you see on the next slide, please, Srinivas. So if you see this, now on the right hand side, if you see this, the script that we run in the smart agent, run in the blockchain through the smart contract. So if you see the time from where 27th May 6:30 and then the time 2, so it's a half an hour window, and the amount of power is 2, meaning it's a half an hour, so it's a 1 kWh, right? And the set price, because PRA wanted to sell that power at a 5 rupee per kWh, so this is what the selling price, and the timestamp and everything is logged in a blockchain. And the meter reading, if you saw the start meter is minus 666.8 because it's a selling the power, so it's a minus, and the ending is 667.9. So which means it is of 1.1 unit that PRA has sold at the 5 rupees, wherein peer B buys the 0.1 unit. So peer B reading, if you see buyer meter reading S and buyer meter reading E, if you see on the right hand side, the last fourth line of this, you can easily see how these meter readings are verified, that how much power is being traded. So all these data are logged in a blockchain, and we wanted to verify physically whether this transaction is verified or not through the energy meter readings, right? So this is the POC that I mean, this specific use case we wanted to narrate here, but we developed many cases when the sun is available, when the electrical drive coming back to the charging station, and with the SOC of 50% now is selling power to the PRC and vice versa. Different use cases we have developed. Just for the sake of understanding, we would like to present only one use case here to understand like how P2P energy trading platform can be developed to empower the consumer having the on-site resources. Moving forward, please. So that's all about the POC or test rig that we developed at IIT Gandhinagar. I would like to quickly present because we wanted to scale it up. Now the people may ask that, okay, you presented to only 3 prosumers. How about the scalability of this concept and the platform? So we demonstrated this peer-to-peer energy trading at CESC with the 30 locations. And if you look at the mix of the consumer, variety of the locations, the 9 of prosumers having a rooftop PV system, the size varying from 10 kilowatt peak to 150 kilowatt peak. And these 20 consumers are the offices and one prosumer having a battery storage, stationary battery storage. So this is how the variety of consumer. Now in the IIT Gandhinagar, we had the Peer A with the Peer B, the different. So now we wanted to scale it up at the utility level. So this is what the P2P energy trading at the CESC. The pilot was conducted in September 2021 to February 2022, and so this time frame, if you see, this caters the at least the seasonality, because the 9 producers having a rooftop PV system, and we know that the solar PV generation is very much seasonal dependent, and also the profile varies over a day in the sun hours, right? So we wanted to cater as many use cases as possible so that we can demonstrate the whole possibility and validate the P2P energy framework. So the second important point here, I would like to mention that this POC demonstrated one-to-one trading, one-to-many trading, as well as many-to-one trading, right? So all persons, let's say 9 producer would like to make the contract to only single peer, that is also possible. So many-to-one. Then only one producer would like to make a contract to multiple consumers or multiple consumers, that is also possible, because that gives the scalability. I mean, that validates how the platform is reliable enough and reliable enough for the large size of the classes, large size of the variety of the consumer and the classes, right? So that is one. The second lesson that we learned from here is like how to fix or how to map prosumer to consumer. Now, while looking at the historical load pattern and the historical generation pattern of the consumer and prosumer respectively, we developed the baseline. And through the baseline data, we said, okay, this is what the right pair of consumer prosumer to make the transaction. And because we have to authenticate, once the contract bids are submitted, whether it's a buy bid or sell bid, we have to validate whether the transaction happens or not. And that validation is coming from the energy meter only. So, but then we have to have a pair matching in there, so that at the end, our objective is to minimize the deviation. There, right? So deviation settlement we have to do. I mean, the utility people understand that how critical is the deviation settlement. If the deviation is very large, it is nowhere possible to roll out this kind of framework, right? So we want to minimize the deviation settlement as much as possible to gain the confidence to roll out this framework to the utility level. So we did this thorough exercise, and based on the baseline energy consumption that we developed through the historical data of 3 months with the 30 consumers, we found that these prosumers are also having a potential to participate in automatic demand response, and that we executed partly with another site, another POC at BRPL, BSES Rajdhani Power Limited. Okay, so this is how. And the second observation that we said observed was that most of the solar PV energy from the solar PV panel is low before 9 a.m. and 15. I mean, that is naturally because whenever the sun, the sun radiation is not perpendicular to the solar panel, certainly you won't get the maximum power. So the maximum power you get from the solar PV generation is between 12 to 2 p.m. where it reaches to the maximum power, right? So that is of course. And the next slide where we see that at the BRPL. So previous slide concludes the use case of P2P at the little larger scale with the CESC. And here is the another use case which attract the prosumers to participate in a demand response. It's an incentivized demand response, and we developed. We demonstrated this POC with a BRPL, BSES Rajdhani Power Limited. We created around 5,000 DR event for 2 objectives. One is a peak saving, and other one is a load shifting. So peak saving potential we know with the thermostatically controlled load, which is split air conditioning that we use at the residential level. we set the automatic temperature control so that without compromising the comfort level of the consumer, residential consumer, we can get the peak saving. At the same time, the geyser we use in a winter. So you can see, the AC we use in a summer, so that helps for a peak saving. Whereas the geyser we use in a winter and that can really help for a load shifting, because we use a geyser in mostly the morning times, maybe starting from 6 a.m. morning once we wake up, and we use a geyser, and then up to 8:30 or so. So that is how the load pattern of the geyser. And we notice that the average relief of around 0.86 kilowatt for a peak saving and 2.08 kilowatt for a load shifting to the residential consumer. Around 25 residential consumers were selected in this exercise. The second takeaway message here is we noticed that around 25% time slot contribute to 70% of the entire day energy consumption. What does it mean? That out of this 96 time blocks, every 15 minutes interval, right? So 96 time blocks, around 20% of time block contributes to the 70% of the total demand. So if we target only that 20% of the time blocks out of 96, so 20% is around 10 time blocks, right? So if we target that time block for peak saving and load shifting, we try to capture most of the potential of ADR, automatic demand response. So this is what we realized. The second thing that this POC we demonstrated that is equally scalable while we consider the locational, geographical location, the different feeder length. So the package that we develop through this project is very much customizable, and we can fine tune, or we can have a retrofit of this the DR product here with a specific consumer specific, basically. So the custom DR event schedule and incentives for the residential and the commercial and industrial consumers. So an overall consumer participation we observed was around 40% during this, because it was the first attempt, and we want to have a more and more participation of such consumers who can really leverage the benefit of incentivized DR event, right? So next slide, please. So here is the video just to demonstrate how the DR event was conducted. Srinivas, please play the video. Sorry, somehow audio is not clear, but nevertheless, it's fine. If it is possible, Srinivas, if you try to do some adjustment. If not, that's fine. Now, let me explain. If you restart the video, please, first. Yeah. Yeah. So we wanted to create the DR event, and the DR event was created, and we said, okay, at 6:15, if you see at the top, it's a 6:14 p.m. And we said that the air conditioning should be switched off at 6:15. And here, if you see exactly at 6:15, this conditioner will switch off. Because of the set temperature, we set at 29 degree or 28 degree, because right now the AC temperature is 28, and we said 6:15, it should switch off. The compressor should switch off, and the air conditioning would contribute in the DR event. So play, please. So this is how we did that. That's fine. That's fine. So Srinivas, that's fine.
Okay. Okay.
Yeah, so here 6:15, this compressor is now, air conditioning is now fully switched off, and the consumer has participated in the DR event and save the and gain the reward, right? So in terms of, because it was an incentivized DR event, so the consumer will get the benefit while participating in this DR event. The next slide, please. So just quick data analytics here. If you see on the right hand side top figure, as I said earlier, the around 10 to left hand side figure, please. The left hand side figure top, where we see the most of the around around 19% or 20% of the time blocks where you get the maximum energy consumption. So this is the slot wise breakup of energy consumption. If we target those the set of the time blocks where we get the maximum energy saving and run the DR event, we can try to get the reward of around maximal reward basically, right? So that is what this metric shows, that where I should basically, for a distribution utility, the critical question that they ask is like, at what time I should run the DR event, and what all sort of consumer I should pick up for the DR event. So this is what this data analytics says for those selected consumers, 20 consumers, what time slot I should pick for executing the DR event, right? Then the next figure on the middle one, we notice that what is the baseline energy usage of all 20 consumers, so that we can find whether they faithfully participated in DR event, because sometimes there may be the false data, and since we record this transaction on in a blockchain, no, so the trustworthy platform, but if any malpractice at the consumer end, that can be figured out through the statistical analysis, and that's how AI/ML integrated platform would really help when we play around with the big data analytics, right? But here, if you see one anomaly is there, keeping that anomaly aside, the otherwise the profile you can see is very well defined, the baseline of the 20 consumers. The third figure, if you notice, is a monthly changes of the energy uses. On a y-axis, if you see, the first figure is for the November month, the second is for a December, and the third one is January. As expected, that we mostly use the geyser in the winter period, which is December. So December, you see how much is the peak during the morning. As I said, the geyser operating hours is what, around 6 a.m. morning to around 8:30 a.m. morning. So there you see the peak. And if we try to shift this load, maybe little early morning, that is what we saw. We demonstrated that shifting in the next month, January, we see the peak get shifted towards the little early morning, maybe around 5:30 a.m. morning or so, and we can make use of the thermal storage capacity of the geyser. And as we know that the thermal, the storage tank inbuilt in the geyser can help to store that heated water for maybe 2 to 3 hours or so. So that storage we can make use for the shifting the appliances uses and reduce the peak. So basically, this demonstrates the peak saving that we realize for all 20 consumers. So when we selected this 20 consumer, we selected strategically having that consumer having a geyser and air conditioning, so we can demonstrate both peak saving as well as the load shifting in case of air conditioning and geyser respectively. Now the figure 16 here, meaning the top bottom figure, bottom left figure, where you see this indicates the success of the DR over a time. If you notice, the blue line, horizontal line, is 100% participation of the consumer in the DR event. At the beginning in August, if you see the rate characteristic, at the beginning at the August, the 70% consumer participated in the DR event, and they continued their participation in the September month also. Over a time in December and January, we see their commitment in terms of achievement. Which means, let's say consumers say, I am committed to save or curtail or save 3 kilowatt of demand during the DR event. But whether that was achieved fully meaning up to 3 kilowatt, or that consumer achieved up to only 2.5 kilowatt. So what was the commitment, what consumer has committed and how much it was achieved. So we try to minimize that gap. As I was mentioning earlier, as a utility, we always try to minimize the deviation. So here it indicates that, okay, it was expected this much and how much actually contributed in the DR event. And this indicates the positive sign, as the commitment and the achievement is as close as possible, right? So this is how we wanted to find, the kind of the success of the DR potential, because we wanted to the end objective is we want to encourage more and more participation, active participation by the consumer in the DR event. Now the last figure here indicates that how confident we are, or what was the validation process, that okay, if we want to have a geyser as the controllable gadget for a shiftable device, how it is closely matching with the energy meter data. So the geyser connected through the smart plug has the metering capability. So we log the data of smart plug from the smart plug wherein the geyser is connected. That data we closely match map with the energy meter data. So because energy meter data at the residence measure the aggregated power demand at the home. That home has the street light, fan, everything other than the geyser. But then the geyser was the one appliances participated in a DR event, right? So we wanted to check how validate that the geyser participation was for a DR event. So that's how, if you see the blue and the orange color chart here, starting from 4:30 a.m. morning to 6:30 and up to 8 or 9 a.m. morning, that's what the typical cycle where we operate the geyser, right? And this is closely correlated with the energy meter data. This gives the confidence that okay, the geyser is the one appliances participated or used for a DR event participation by that consumer. So this is for a typical consumer or one selected consumer from that set of 20 consumers that we selected for this POC at BRPL. So with this, what we learned, the lessons, just to summarize the discussion related to the peer-to-peer energy trading, then automatic DR event that we demonstrated as a part of the project. We started with the three prosumers with the POC at IIT Gandhinagar. We roll out this platform with a CESC with more consumers, and then more consumers and prosumers, and then the another program that incentive-based ADR that we demonstrated at BRPL. With that, let me complete my session, and I would request Mr. Srinivas to take it over. Thank you very much.
Yeah, thank you, Professor Naran, and thank you, Professor Garg. Now, in the next 15 to 20 minutes, I would like to walk you over what blockchain is and what other use cases we have discussed with the industry, and maybe we're working on using blockchain for the energy sector. So what blockchain is not, first, maybe that I'll cover, that blockchain is not a Bitcoin or a shadow economy or a cryptocurrency, not an illegal activity at all. And it is also not merely a replacement to a database. Okay, it is a technology which kind of allows anything of value to be transferred digitally from between non-trusting parties. Okay, and it can be used to establish the provenance of any asset, that is where it generated, how it tracked up to you, right? It can be used to reconcile party records of multiple parties in real time. And it can also, business logics can be embedded in the form of smart contracts, and it can be executed when a certain criteria is fulfilled. And to just give you a gist of where blockchain is today, if you go back maybe 20-25 years ago, we still saw phones like this, which were landlines, and we didn't have a concept of maybe mobile communication as much, right? And then suddenly we had a shift from the 1 rupee per minute kind of thing to data. Right? All of a sudden, the game from changed away from per minute billing to data billing, right? And we had an explosion in technology through CDMA, GSM, 4G, LTE, 5G now, right? So the only thing I'm trying to say is that, okay, power sector is where maybe the telecom sector was 25 years ago. It is just at the cusp of shifting, just at the transition phase. So right now, the idea of blockchain is born. We are testing some very fundamental, some basic use cases of blockchain through cryptocurrencies, through other forms of digital assets. And so the next thing is that once the blockchain technology further matures, we'll have a lot of different types of blockchains, maybe for one for energy sector, one for supply chain, one for banking and finance, and then there could be specific applications built on top of this blockchain. And the key features that make blockchain very valuable are that one, it is shared and trusted in the blockchain network. There is immutability, which means that whatever records are put in the system cannot be tampered with, and only someone can append or can add further on the distributed ledger. Okay, we don't need any intermediary to actually do the settlement if our smart contracts are built right. And since there is no central point of failure which can be exploited, it gives a more robust, more secure system. This is something which is very, very crucial for the energy sector, since we have seen over the past few years that there have been attempts to hack the distribution websites, distribution databases, and have led to a few downtime as well. Okay. The structure of blockchain is that we have a place to store transactions, decisions in a distributed ledger, right? And then once we have a agreed upon consensus mechanism between the participants, between the different nodes in the blockchain mechanism, that's when we can start executing smart contracts, executing any business logic. So first we need for a few players to come together, agree on a blockchain network architecture, agree on the consensus mechanism, and then we set the basis for a trusted blockchain where all the participants know that, okay, whatever I am seeing is exactly what the other person is seeing, whatever power I have on the blockchain is exactly what the other person has, right? So once the blockchain network and the fundamental consensus mechanism are agreed upon, then we get into actual building of applications using the blockchain. So there are three primary types of blockchain. One is a public blockchain, wherein the standards are, for example, Bitcoin or Ethereum, which started as a large consortium. Many people anonymously participate or join in and register into the public blockchain, and there is all the data that is visible to you as a node is visible to everyone else, right? And so it is completely open. Anyone can write or create a transaction or create a block. Anyone can read any block. There is anonymity, of course, because you're not identified by name or anything, but there's a unique digital identity through which you are identified. So that gives a high level of anonymity. But on the other hand, the transaction speed and is slow, which may not be very conducive to a lot of applications, for instance, financial applications. And decentralization, it is completely fully distributed. Then we have consortium blockchains like R3 Corda, Hyperledger as well, wherein the blockchain is not open to everyone. There are specific parties and groups which can participate on the blockchain, which can add and write transactions to the nodes. And also what this means is that it is not fully distributed like a public blockchain. It is partially decentralized. Okay, but the advantage here is that it is fast and which means it may be suitable for a lot of other applications like financial transactions, wherein you need like lakhs of transactions happening in a second. Then there is a third kind of blockchain, which is private blockchain. So we are going from a fully open system to a closed system in steps. And here the control is very is governed by a few nodes, and it is not open to everyone. It is very restricted. But and what that means is, you know who the third party is, who is posting the transactions, who is reading, accessing the data. And but then the benefit is that it is extremely fast. Now, the reason I brought these things up is that basis the application, we need to choose a particular type of blockchain. Not all blockchains are suitable for every kind of application. Okay, so for instance, for peer-to-peer energy trading, one might say, okay, we will go with a completely public blockchain. Maybe not. Okay, a consortium blockchain may be a right blockchain architecture for peer-to-peer energy trading. Whereas if you look at maybe a supply chain use case within your factory, or within multiple locations of your organization, then a private blockchain may be more suitable. You probably don't even need to go for a consortium blockchain where you have 10 different parties, right? So there are different levels of decentralization, and each one has a different cost of operation as well. Not just the access levels, but the cost of operation as well changes significantly. A private blockchain may be lower cost compared to a completely public blockchain. Okay, so in this slide, what I wanted to explain is that there is a clear line of distinction between blockchain, a web application, and a database. Okay, they are all three different things, and they need API integration between them to work seamlessly. Okay, so in a web application, what typically can be done is user management, or in terms of energy sector, I'm just using the energy sector terminologies, a schedule management, scheduling engine, baseline determination, historical transactions, DSM tool, or reporting financial settlements. So these are all business functions. So they can be handled properly in a web application, wherein the speed matters, wherein the user interface has to be lightning fast and convenient to use. You may have a mobile, you may have a web, you may have a tablet PC, multiple different touch points through which the consumers engage. And then the blockchain is where you store the most critical transactions. Not all the transactions and information in the web application need to go onto blockchain. Whatever is needed for settlements, whatever is needed for entering into smart contracts, validating smart contracts, right? And whatever is needed to form the data repository, which may be required later on for auditing purposes, only certain pieces of information could go into blockchain. And then we have we also could integrate it with a regular database like NoSQL database or MySQL database, wherein we can use that data for a lot of forecasting or any other searching, any other AI, ML, and other applications could all run on a traditional database. Okay, for that you don't need to overburden your system, your blockchain system. So all the three have to work hand in glove to make an application run seamlessly. So what are the value adds of blockchain? The key value adds of blockchain that we have been able to identify for most of the energy application is one, a real-time consensus. That is, traditional databases, though we may think are even if they're decentralized or distributed, they don't have a off-the-shelf implementation of real-time consensus. That is, the data is first hitting one centralized database, and then it is kind of spread across to the cloud network. Okay, so it is syncing. It is not in consensus at the same time. Whereas blockchain is built on the concept of real-time consensus. That is, first whatever transaction is there is reflected across the blockchain network, and once the consensus is established, only then the block gets created. Okay, so then that's how the blockchain is built. Cyber security, it offers the highest level of encryption, and since there is no single point of failure, and there's no single owner as well. In fact, you need to put in enormous amount of effort and power to gain control over a blockchain network, that it becomes financially the user, even if he's trying to hack a blockchain system, is financially disincentivized to do such a thing. Okay, so it offers the highest level of encryption and security. There is no financial incentive for someone to actually hack a blockchain system. Third thing is tamper-proof. But it is tamper-proof by design, and records cannot be overwritten. They can only new records can be added. That means that you know when a particular record was created, who created it, what was the values in or parameters in that record, and how they have been modified over time by multiple users. Okay. Reconciliation, measurement, and validation can be accomplished through blockchain in real time. Settlement can be automated. All the financial transactions can happen through blockchain in real time. Okay, and finally, confidence. Since it is consortium managed, consortium driven, say utility company, it's the RLDC, SLDC, the regulator. So all these people can form the consortium for the blockchain and agree on what should be the typical architecture, and what kind of consensus mechanism is to be used, or what are the key data that will be put in blockchain, so on and so forth. So again, it is a community effort to first define the blockchain, and then the burden of managing is democratized over the managing the blockchain network is democratized over the consortium. Okay, so we know that no single person owns or is in control of the entire system. Now, after having run several pilots, having had several discussions with a lot of energy sector players, there are a few things that we highly recommend that one has to consider when building an application using blockchain. The first thing, of course, is the type of blockchain network to be used, whether public, private, or consortium, right? I've explained some details earlier. The second thing is, what are the data size? How much data are we trying to put in a block, or how much data are we trying to write in a transaction, right? So for instance, we discussed a scheduling use case, grid scheduling use case, wherein we have multiple fields of data coming in from the generators, coming in from the utility companies, for instance, declared capacities, the drawal schedules, the dispatch schedules, the entitlements, kind of thing, which means that the amount of data going into a block in a blockchain is pretty high. It exceeds the 96 KB, which is standard for Ethereum. So what it means is that we either need to break it and put it in multiple blocks, or we need to maybe only use a very critical information on the blockchain and put the others on off the blockchain. Okay, so there are multiple solutions available for managing such data splitting and data sharing between blockchain and off-chain. Okay, and we have specifically discussed these use cases with a few players. The third thing is time for committing transactions. As I said, a truly public blockchain, the time it takes to post a transaction may be even up to 10 minutes in some cases. Okay. Whereas a end user will not be waiting for the transaction to be posted and commit and a receipt coming to you on your mobile application. Think about it, you holding your mobile and waiting for a confirmation on the transaction that you just made, right? We need to build asynchronous web applications. For instance, just to make it more real life, when you use Google Pay or something else to make a transaction, sometimes you submit the transaction and it says, okay, your transaction is getting processed. We'll let you know once it is successfully completed. Okay, so that is asynchronous. The receipt or confirmation may come a couple of minutes later, but the transaction record has been first generated in a local database. So when building blockchain, this is a very, very important thing. We have burnt our hands a couple of times, that we need to look at the amount of time it takes to commit a transaction and build an application in an asynchronous manner. Finally is transaction charges. Transaction charges to create a record in blockchain, for instance, Ethereum, it consumes maybe 5 rupees, 10 rupees to post a transaction, right? That depends on the amount of data, how many kilobytes of data are you putting in, and the number of transactions you are creating in the blockchain, right? Reading data from the blockchain does not consume incur any charges, but writing data to a blockchain does. Okay, so we need to be very even of that fact that how many transactions are we creating and how much amount of data are we writing per transaction. Both these two determine the transaction charge. So these are a few considerations for building a blockchain application. Now, since we are above the scheduled time, I will very quickly run through the few use cases. Right, peer-to-peer energy trading, I'll completely skip it because Professor Naran has covered it in great detail. I don't need to do anything there. The grid scheduling, I've briefly touched upon that there are multiple stakeholders, RLDC, the generation plant, SLDCs or utilities, and then the generation plant first submits a declared capacity, the RLDC releases the entitlements to the consumers, SLDCs and the generation plant, and then the SLDCs further come back with the drawal schedule. Right. So such and these schedules, there could be multiple schedules. What we understand is there could be thousands of schedules created in a particular day for all the 96 time slots. So we need to make sure that there is enough confidence that there is no data tampering happening anywhere in between, and whatever you have submitted is exactly what the RLDC is seeing for generating the schedule towards the end of the day, right? So there are multiple revisions, more than 1,000 schedules in a day. Chances of error are pretty high, and there is lack of visibility to all the stakeholders in the current system. And so in the if we say that POSOCO is the system operator, then the burden of operating and maintaining the platform is probably on the main system operator. So blockchain helps democratize this process and is a very relevant technology for this use case, right? And this is how the architecture would be, that the dispatch schedule is submitted into blockchain. The drawal schedule is also put in blockchain. Metering and validation happens towards end of day for deviation settlement mechanisms, right? And then so this is where the blockchain is, and what are all the processes that happen through the system, right? And so the third use case is intra-state trading. That is within a state, between utility companies, for energy trading to happen, in intra. It could be intraday or interday, right? Wherein the generator and the consumer agree for energy trading, and then it is facilitated through the power flow happens through the CTU or STU, and is facilitated by a power trader, right? So buy and sell bids are placed by the generators. There's bid matching happening between the generator and the consumer. Contract is created through the platform, and deviation measurements happen, and trade is settled. Now, this is, I would say, a modified use case of peer-to-peer energy trading, where we have not just a prosumer and a consumer, but we also have a few other players like CTU, STU, SLDC, and a power trader in the entire system. Right. Again, here we believe consortium blockchain is an ideal tool for this use case. It enhances cybersecurities. It helps in creation of smart contracts. And some of the technical challenges here are the ability of smart grid availability of smart grid infrastructure, and integration of blockchain with multiple systems. That is, each utility company may have a different database system, so blockchain needs to be integrated with multiple utility systems, right? So those are the technical challenges. On the business challenges, we have to see how much data cost is there for blockchain, what kind of infrastructure may have to be replaced, and getting all the stakeholders onto a single page in terms of the blockchain technology. Right? Another use case, interesting use case, which we discussed, is a energy service company platform, wherein an energy service company typically is looking at energy savings, and how do we monitor the performance of an ESCO company. So there are multiple stakeholders involved here as well. The utility company, which is supplying the power, the energy service company, which is responsible for technical performance and delivering the energy savings, and the user who is having the energy assets, who is managing the energy assets, and is trying to ensure that the energy consumption is reduced, right? So there are multiple sources of data from the user, from the DSO, and from the energy service company. These data of smart meter, of the home energy management system or smart agent, they all come into multiple data platforms, whether it is blockchain, cloud systems, databases, on which there could be data analytics run at various depths and at various granularities, right? At whether we are taking the data only at a premise level, at a appliance level, at a switch level. So various levels of granularity of data could exist. The reason I'm saying is this leads into the concept of a data lake, wherein data is coming from multiple sources. We need to ensure that the data is highly anonymous. We need to ensure that the data security is available, and that consumers are come forward and confidently share the data with third parties to realize the true value, right? So there could the value comes in terms of demand forecasting, behavioral insights, actionable items, preventive breakdown, maintenance. So these are multiple applications of the data, and it is only possible through a combination of IoT, blockchain, AI/ML, all of them coming together, right? So data monetization, data economy, and yeah, business transformation can happen only when these technologies come together. So that's something that I wanted to highlight over there. Now, after having kind of gone on a monologue for an hour and a half, I would really open up for a discussion, and we are open for taking any questions from the audience.
Thank you so much, Srinivas sir and Dr. Naran, for your presentation. To all the participants, I would like to announce that the panel is open for discussion. If anyone is interested in asking any query or interacting with the expert, he or she can unmute themselves and ask the query. My humble request to please go one by one. Does anyone has any query?
Most of them are muted. I don't know if they can unmute themselves.
Sir, I've allowed them. They can unmute themselves.
Okay.
Sir, this is Vinay Goyal. May I ask?
Yes, sir. Maybe can you introduce yourself?
Sir, I am Vinay Goyal. I am working in a hydropower department in Toshiba, India. But I am joining this webinar in my personal capacity due to my interest in new technologies in power system.
Okay.
Actually, in the last 12 years, I've spent most of the part in my profession in generation technologies. So what I understand from the webinar that the blockchain technology in power system, it is like democratizing the basically consumer sector. Right now, there are a lot of upgradation in generation side, transmission side. But what we see that the way the consumer are consuming the electricity, it is like from the last 30-40 years, it is in the same way. Like there is one wholesaler and there is one consumer, and you are bound to take the electricity from the one wholesaler, and you are dependent upon him. You have made a contract, but the wholesaler is not in any way obliged or guaranteed you like amount of electricity or the time of electricity. Like for by this time to this time, I will pay you electricity, whatever you have contracted me. And if I don't provide you the electricity at that particular time, I will make some concession or I will be penalized. This kind of thing is not there. So what I understand from the blockchain that as a consumer or as a factory owner or as a retail consumer, I will have the option to buy electricity for many people in my network, and in the like different price range also. I will not be dependent on one wholesaler or one electricity provider. This is my first understanding. Please tell me if I'm wrong or I'm partially right. And the second question is, the blockchain will provide all the facility on a contract level, like from whom I'm buying the electricity, the data level. But behind the scene, the actual power system network, I'm talking about the wires and cables and how the power electricity is reaching from the generating station to our home. On that particular network, in particular in the distribution stage, that like sir in his case to demonstrated that we will using a lot of controller and control wires to enable that the power flow in the network will be as per the contract executed on the data bus. So my question is this, we need to improve or we need to upgrade our from the data bus, which the blockchain will be in the data bus, which will execute the contract. And it will require a lot of improvement and upgradation and technology on the, you can say, electricity bus and control bus also. So that is my question. First question is that it will be beneficial for the consumer angle. And the second question is, it requires a lot of technologies and the investment on the electricity bus also. Like control, like my home and my neighbor home, they don't have control wire, they don't have any interconnection, that kind of thing.
Okay, so I might try to answer the question, but by all means, Professor Garg or Professor Naran, feel free to intervene. So in terms of upgrading, I'll go with the second question first. In terms of upgrading the infrastructure, yes, you don't need to lay cables between. So if two participants have to participate in peer-to-peer energy trading or do demand response, we don't need to add any more wiring or cabling between them. That is for sure. Okay. So we are going to use the existing grid infrastructure itself. What is needed though is the assets. So if you're saying I want to control my AC, I want to use a EV charging vehicle to grid, whatever energy assets you would have naturally as you are a homeowner, we are trying to offer more value using the existing assets. Okay, what you would need additionally is, since you want to, if you want to have real-time settlement of trades, you need to have smart meters which are communicable. That way you can settle the trades in real time. But if that infrastructure does not exist and you do not have the capability to get reliable data in real time, we can even do the settlement after the fact. Post facto settlement can be done. Okay, but it just makes the experience a little it reduces one notch, because in today's day and age of instant gratification, you just want to see, bhai maine 10 kilowatt becha, bika kitna paisa aaya mere bank mein, right? You don't want to wait for 1 day or 2 days and then realize what happened to your trade. Okay, so the requirement in terms of grid upgrade, I think at a HT level we already have the AMR, AMI. There's no further upgrade probably needed. At a end consumer LT level, certainly we need proper smart metering for real-time settlement. The second question, in terms of democratizing the power, is it own? Does it unduly give power to the consumers? I believe that was your question, that okay, still blockchain is only impacting the end consumer layer and it is not probably impacting as much on the generation transmission kind of thing. For that, what I would say is we have shown this particular use case of intrastate trading. We have shown the use case of grid scheduling. These are particular use cases wherein generation is there, wherein utility companies are involved. These are at a systems level. These are not any longer at a consumer level. Okay, but yes, blockchain as a technology does not differentiate between a utility company or an end peer. Okay, all it cares about is, okay, who is on the network, who has access to what data on the network, and who is doing the validation of the data. So it is more about who are all the peers on the blockchain network, rather than really talking about the. So it brings the consumer to the same level of authority as any other player in the blockchain network for a particular network. Of course, we could always have private networks wherein you can define hierarchies and say, okay, the RLDC has a certain level of hierarchy and certain level of data visibility compared to the other participants on the blockchain network. Even to that extent, it is possible. Hopefully, I have answered your question, but Vinay sir, if you have any
sir, I think on my part, it need more study and first self-analysis before asking the question, because it is a little bit overwhelming for me as a new technology and its application. So I need to do more study and more self-analysis before asking the question.
Certainly feel free to drop us a message or we can take the discussion offline and I'll try to clarify. Okay.
Thank you, sir. Thank you very much.
Yeah.
Anyone else with any query? Okay. Sir, shall I pop one query if you don't mind?
Yeah, absolutely.
Sir, as blockchain is quite a newer technology, and as far as I have learned, one of the biggest advantages it has, it's the transparency and the security it is providing. So, but being such a new technology, do you think we can rely on it that it can decentralize such a big grid system that India has?
Okay. So my answer to that question is definitely we cannot overnight have a transformation from the existing kind of network to a blockchain network. They have to run parallelly, right? So whatever systems and mechanisms are there today, they of course are serving the purpose and are fairly adequate for the current usage, right? The problem is when you have an enormous amount of distributed energy resources and transformation happening, and the power of say if I'm a energy generator, I would naturally want to manage and maintain my energy in the way I like it, right? So as the power goes more and more towards the consumers, at that time we need to rethink the way we are currently transacting on the energy grid, and that is when blockchain becomes important. So what I'm trying to say is that today we need to start laying the foundation one by one, and need to run a parallel system for a few years, and as the system matures we transition. We by no means I'm suggesting that we just flip the switch and tomorrow move over to blockchain. Okay, right?
Okay, thanks a lot, sir, for that. Just one more query. Just wanted to confirm, like India has 2-3 use cases of blockchain in power trading and everything. So, like globally, also the world is on the same page as India, or they are much more ahead of us?
It's a tough question, really. We hear a lot. We have also discussed with a lot of players abroad and in India. What I realize is they're probably slightly ahead, but not in terms of technology. I wouldn't say, but in terms of technology, they're way ahead. In terms of the infrastructure availability, they're certainly ahead. In terms of the regulations and use cases possible in their markets, they're ahead. Okay, but in terms of blockchain technology itself, I believe we are as good as them. Okay, in terms of any software, hardware, available technologies, we are just as good as them. But in terms of infrastructure, grid infrastructure availability, or in terms of regulations, policies, they may be slightly forthcoming. Dr. Naran, you might want to pitch in with your experience as well.
Not much additional points, Srinivas, you have covered already. Yes, so in terms of technology, yes, we have also built up the infrastructure to have a right technology integration. And in terms of the blockchain and the data science, AI/ML application, also many sectors, including electricity sectors, have implemented the projects right from the pilot project to and the rollout to the field integration. So, like whatever Srinivas said is like I'm aligned with that. So, yeah, nothing much to add on what Srinivas said actually.
Okay, thank you so much, sir. So to all the participants, if there are no more questions, we shall be ending the session. Okay.
And if
yeah,
there
please.
are any questions after the training today, certainly by all means, as I said, I would request you, Shashank, to facilitate those questions. We would be more than glad to answer them. Okay, one-on-one.
Thank you so much, sir. So kind of you. So to all the participants, as Srinivas sir has already announced, if there are any post queries, you all can mail me the same, and I shall be facilitating the same, and we will get back to you as soon as possible with the best of answer possible. So, sir, one request I had, as you know, our main intention was to just organize a knowledge sharing session to open the mind of people, and because blockchain has one side of the brain of most of the people is having a negative side for blockchain because of less knowledge about the subject and all. So we were hoping to quite attract a lot of audience to also move them move their brain from the blockchain. It's just not related to cryptocurrency, but also a lot of more applications. So we were just hoping if we could put this session in YouTube, if you don't mind.
I don't have any concerns. I think, Dr. Naran?
Fine with me as well.
Yeah.
Okay, thanks a lot for that, sir. Yes, sir. Okay, so with that, we'll end the session today. First of all, I sincerely appreciate Professor Amit, Dr. Naran, and Srinivas sir for agreeing to our request to organize this session. It's really a big shout out to you guys. Professor, I still remember when I talked to Dr. Naran and with this proposal to organize this program, and without a second thought, he was ready to conduct this session. So really thank you a lot for sharing your experiences on the subject here. I'm sure the topic was justified and was really well explained by you guys. Also, one more request I was having, if so can we share the presentation with the participants that was made today?
Yes, I certainly don't have any concerns with that either. Okay, not a problem. We'll come back to you. Maybe just have an internal discussion and come back to you on that. Okay, there may be a few slides we might have to sanitize. Otherwise, it should be okay.
Sure, sir. Sure, that will be great. So thank you so much to all the participants also who joined with us in this program. Thank you so much for your support, and big shout out to IIT Gandhinagar and IIM Ahmedabad for their support to organize this program. Thank you, sir.
One last request here is,
yes,
if there is any feedback as well on how today's session went, if there's any suggestions from the audience, kindly note it down and communicate so that we can adapt the current presentation. Right? We understand that we might have gone too much into the technology side, or we might not have touched upon some of the things that the users were expecting. We certainly need that feedback.
Sure, sir, sure. So to all the participants, we are hoping to get your honest feedback on today's and yesterday's session. You all can get back to me in my email address where you all got registered. So with that, thank you all for joining. So shall we end?
Yeah, thank you.
Sure.
Thank you.
Thank you.
sir. Thank you very much.
Thank you, Dr. Naran. Thank you, Srinivas sir. Thank you, everyone. Bye bye and take care, please.
Thank
Good night,
you.
sir.
Bye.